So let's start. Welcome to our afternoon session. We will start with a talk by Frank Coronado from Zurich on bootstrapping the n=4 super-Young-Mills correlators.
Thank you. Well, first I just want to thank the organizers for giving me this chance to present my work. Today I'm going to talk about this work we prepared with Simon, Ankoy, and Sarah about bootstrapping correlation functions in planar super-Young-Mills. So super-Young-Mills is our favorite theory because it's the simplest gauge theory in 4 dimensions, and due to its many symmetries, and especially in the planar limit, we believe it's solvable thanks to integrability and thanks to the big work of this IGST community. We now have managed to compute many observables, at least in the planar limit, where we have this integrability. Super-Young-Mills also serves as a laboratory for testing non-perturbative techniques that have wider application, such as the conformal bootstrap. And in fact, there are some recent works on using conformal bootstrap at finite number of colors by Shai. Also, in the recent years, there's been progress on combining this powerful conformal bootstrap technique and also the integrability of the planar limit to determine the OP data of line defect CFT embedded in super-Young-Mills. And today, I'm going to follow this same philosophy of combining conformal bootstrap and integrability, but now I'm going to address OP coefficients of local operators. So the protagonist of today's presentation is going to be the scaling dimensions of the local operators, the OP coefficients, and also the 4-point function of the stress tensor that is dual to this string amplitude in ADS. OK, so regarding the first set of data, the spectrum of the scaling dimensions, that is a problem that it's solved. We can consider this to be solved in the planar limit. And that means that, for instance, we have complete control over the dimensions of single trace operators. And at any value of the coupling, non-perturbatively, we can compute, let's say, numerically, what is the value of the scaling dimension and how it evolves all the way from weak to strong coupling. This plot has many years already. And since then, there's been huge progress, also in part thanks to the great work by the group here at King's College, that now there is a bank of data for the spectrum of many of the non-protected operators. So this problem is solved. But now we would like to address the next set of OP data, which corresponds to OP coefficients. So here I'm going to consider the simplest OP coefficient. First, I start by considering the stress tensor multiplet. I consider the OP of 2 stress tensor multiplets here. We pick our favorite component with this multiplet, which is this operator of dimension 2. And in the OP, we have some singularities, which are controlled by some operators and their OP coefficients. For instance, here we have the stress tensor itself appearing in the OP. And then we have other type of operators, which are non-protected, such as Konishi, which is a single trace operator, and then also this other type of non-protected operators, which are called double twist operators or double traces. If we were to address this problem at finite number of colors, we actually wouldn't be able to really distinguish between single and double traces. In fact, there will be a mixing, which we can maybe see in this figure where, let's say, we start on the free theory at g = 0 and start following Konishi, which starts its life with dimension 2. And then we start raising the coupling, and the dimension of Konishi also starts growing until it finds this operator that has dimension 4. And when that happens, there is some phenomena that is known as level repulsion, which is that there will be a mixing, which will be resolved. And then these 2 trajectories are going to move away from each other. And the new operators on these outcoming curves are going to be actually admixtures of single and double traces. And this is going to keep happening as you keep making the coupling grow, and these dimensions also grow. We'll meet other double twist operators, and then we will have this complicated mixing as we move here in the coupling. But in this talk, I'm going to focus on the planar limit, a large number of colors. And in this case, we won't see the level repulsion. We will just have what we call level crossing, which is that now the single trace operator will stay as a single trace without mixing with the double traces. And here, this red line will represent the curve that Konishi follows untouched. So it's a smooth curve, and it just crosses the place where the double traces are. That is the plot for the scaling dimension. However, there is still evidence that this mixing could happen, and this evidence can be found at the level of the OP coefficient. This OP coefficient will have singularities exactly at those points where this mixing could happen. So it means that this OP coefficient is not such a nice quantity. It has some singularities. However, we know the position of those singularities, so we can multiply by some factor that removes them all. And also here, I'm also multiplying by the asymptotics, removing the asymptotics that we can learn from the strong coupling limit. And we define a much better behave normalized OP coefficient. Now, what do we know about this OP coefficient? Actually, there are many results, perturbative results on the two corners of the coupling at weak and strong coupling. And from our definition and these results, we can see that our normalized OP coefficient should be some smooth curve that starts at 2 on the free theory, and then asymptotes to 1 as we go to strong coupling. Here, these curves correspond to the perturbative results, and of course, they are only to be trusted on the regime of validity, but then here in the middle, they just become pretty bad, and it would be nice to actually find what is the smooth curve, just like we did for Konishi in the past. So this would be something that we can call that we also are solving for the OP coefficients of the single trace operators. Of course, thanks to integrability, there are some methods, non-perturbative methods, that we can use, such as the hexagons or the separation of variables. And we already heard about the hexagons from Ben yesterday, and we will hear more about them from Alessandro in the next talk. And we will also hear from Carlos about this separation of variables on Friday. It is likely that in the near future, these techniques are going to be the ones that will allow us to find such a smooth curve and have complete control over this OP coefficient at finite coupling. But today I will have a more modest goal. My goal will be to use conformal bootstrap to place bounds on this OP coefficient. So for a certain value of the coupling, I will try to find what would be the minimum value and maximum value that this OP coefficient can take, provided that it must satisfy some physical constraints. So what we will find here, interpolating between weak and strong coupling, will in fact be a band of allowed values. And the dream is that by pushing this program, we can eventually close this band and find the exact curve that interpolates. So that's the goal for today. And the method I will be using to achieve that is called the conformal bootstrap. And to introduce this method, I need to upgrade to a 4-point function, now a 4-point function of the 4 protected stress tensors. And I consider different OP channels that allow me to decompose this operator into a sum of infinite number of intermediate states. This is the S and T channel, and because the 4 operators are identical, then the intermediate states flowing are the same in both channels. So we have 2 types of decompositions that should be equivalent, and for instance, this decomposition will be a sum over all these intermediate states weighted by their OP coefficient times the conformal block that is fixed by conformal symmetry. And then we have another equality from this side, identical, but now with the conformal block in a different channel. And because these 2 must be the same, then we get an equation, which is an equation for the OP coefficients times these functions that are well known. And this equation should hold for any value of the cross ratios where this decomposition is convergent. And that means, in principle, we have an infinite number of equations, but also for an infinite number of unknowns. One of them will be Konishi, but also there will be other higher energy states that we also don't control. So the goal of conformal bootstrap is to take advantage of this equation to fix the OP coefficients. That would be the ultimate goal. But if not, maybe find a way to learn about them by maybe placing bounds on them. In order to do that, I introduce something that we call a functional in the space of cross ratios, let's say. So this just corresponds to some linear combinations of this difference of conformal blocks that appear on the crossing equation. And we use this linear combination picks certain pairs of cross ratios. In fact, this could be an infinite sum if we wish, but we will keep it to be finite. And we use this functional to rewrite the crossing equation as some sum rule. A sum rule that we organize as a contribution from the protected part, which are operators we know pretty well, and then the no protected part, which we don't know at all. And this equation is, well, the way it's given is like that the contribution from the protected part should be balanced by the high energy part that we don't know. Here we are also isolating Konishi and separating it from the other higher energy states, the ones with higher scaling dimension. Now imagine we were lucky and we are able to find these alpha k coefficients, just a finite number of them, such that we construct a functional that evaluates to 0 at all the states that have dimension higher than Konishi. If we were lucky and we find such a functional, then we wouldn't care what are these values of these OP coefficients, because this contribution would be 0, and then the OP coefficient of Konishi will be just determined by the evaluation of the functional on the protected operators, which we know pretty well. So that would be the ultimate goal, but of course that's a bit dreaming to be lucky and find such a linear combination that does that job. Something more modest than that would be to consider that let's try to find a linear combination that at each state above Konishi, it evaluates to something positive. And then given that this OP coefficient squared due to unitarity should be positive, then we can say that this quantity that we don't know is positive, and that should be balanced by this part here. Now, if we further demand some extremization of the evaluation of this linear combination on the protected part, then that will allow us to place bounds. And we also will normalize the action of this functional on Konishi to be +1 or -1, depending on whether we want to find an upper bound or a lower bound. So this will be the algorithm we will be following, trying to construct a functional, trying to find these coefficients, such that we construct a positive functional on this side of the spectrum, and it's extremal. It takes its maximum value when evaluated on the protected part. We have many advantages to carry on with this program in super young mills in the planar limit, because as I described, we know the spectrum, we know the exact spectrum. So when we are going to demand this positivity, we don't have to think of a continuum as we will usually do if we don't know what is above. We will just demand some continuum and demand that the function is positive in all this continuum. But because we know the exact positions of the spectrum, then we can demand positivity just at those exact positions. So then the functional could be a function that is positive at those points and even is allowed to become negative in between. So those are less constraints on the functional, and typically that result on better bounds when performing this optimization problem. So the spectrum is known, but that's the spectrum of the single traces, which is known. However, there is a caveat, because in this OP decomposition, the double traces still survive. So, and that poses some difficulty. So let me say some words about these double traces in the OP. So because we are considering the planar limit, we think of the 4-point function as being some series, right? It's stratified as the leading term at large n, and then the 1/n corrections. And in fact, the actual leading term just corresponds to the factorization of the 4-point function into two 2-point functions. This is known as the disconnected correlator. And already here, if we try to see what are the intermediate states, what we will find will be only these double twist operators or double traces given by these composites with some derivatives. And the OP coefficient of those double traces in this normalization I'm using, they are of order 1. Then we can go to the next correction in 1/n. That's what we really call the interacting part of the correlator. This is the planar connected correlator, and it appears at this subleading order. Here we have this connected, the 4-point function represented by this connected worksheet. And we now perform the cutting, and now is when the single traces appear for the first time. Now they come here with OP coefficient with this subleading with respect to this disconnected part. But we also have the double traces, because there will be 1/n corrections to this leading term. So they are appearing here. And because they are corrections, even the sign is not defined. So that poses a problem for our optimization problem, because that relies a lot on having some positive OP coefficients. Besides, also, the position of the spectrum of these double traces is, so far, we have not been able to determine by integrability, so that also poses some difficulty. If we were to do this problem at finite n, such a problem wouldn't exist, because we would start. There won't be this stratification, right? So we will start right away with 2 positive coefficients. But because we're going to isolate the planar connected part, then we have this issue of having this subleading term with no sign, with no positive sign necessarily. So what I'm going to describe now is a way to circumvent that difficulty, to find a way to get rid of these double traces and still get some crossing equation or some sum rules that only depends on the spectrum of single traces, which we know pretty well, thanks to integrability. Now, the way I'm going to get rid of these double traces is by using what we call dispersion relations. This is just based on the fact that if you have some analytic function and complex plane, you should be able to reconstruct that function from the knowledge of its singularities and discontinuities. So the best known example is the case of the flat space amplitude that you can reconstruct from an integral over the imaginary part of the amplitude. And just like this result that is well known, there is a similar dispersion relation that you can write in conformal field theories. You can reconstruct the full correlator just from the knowledge of its double discontinuity, where here, just like the amplitude, actually the correlator also has a similar structure where these branch points correspond to the OPE limits. And this double discontinuity is a simpler object. Now, this should be integrated over some kernel that is something complicated, but has been worked out, so the formula is complete. And this is advantageous for us because now, when we are going to, if we plug in here the OPE decomposition of this 4-point function inside the double discontinuity, this will, after performing this integration, this will result in a new decomposition of the 4-point function. And this new decomposition will depend now on this double discontinuity of the conformal block, which will define for us what we call dispersive blocks or Polyakov-Regge blocks. And the advantage of those blocks with respect to the ordinary block is that they contain extra zeros. And these extra zeros are exactly at the position of these double traces or double twist operators. In fact, in more detail, if this is a non-protected operator, a non-protected double trace operator, this will be proportional to the square of its anomalous dimension, and that is further 1 over n suppressed. So in fact, because it becomes more subleading, we can remove it from the planar order. So now this results into a new decomposition of the correlator, which is a sum that is saturated only by single traces with their OP coefficients times now the dispersive block or Polyakov-Regge block, which replaces the ordinary block. So this is, from here we recover the full correlation function just from a sum over single traces. This is not yet crossing symmetric, so we can still demand crossing symmetry, and we define this function x to be this dispersive block in 2 different channels, and we get now an equation which is a sum over single traces, but in fact not only, even more restricted than just single traces, it only depends on non-protected operators, just on long multiplets. This is still not desirable because, as I described some slides ago, in order to carry our optimization problem, then the part that we need to extremize is the protected part that we know pretty well. And this sum doesn't contain it. This sum is not a sum that balances low energy protected operators and high energy non-protected operators. It just is a sum rule that balances non-protected operators among themselves. So in order to carry on with our optimization problem, we need something more than this sum rule. And fortunately, there is a way to construct such sum rules. And this comes from this result of which is known as integrated correlators. So an integrated correlator is defined as some integral over space-time or over all the cross-ratio space with some measure that makes this integral convergent. From here, you get rid of the space-time dependence, and you just produce a number that still depends on the coupling. Thanks to supersymmetric localization, in the market there exist 2 measures that we know, which we know what number we obtain thanks to a supersymmetric localization computation. So now we can plug in here our OP decomposition and obtain a sum rule, which will now be a sum over these OP coefficients times this function, which will be the integral over the dispersive blocks. And this will produce this number, which actually, thanks to localization, can be computed exactly. And in the planar limit, is just given by this integral over Bessel function, so we can really have good control over any value of the coupling for this number. In fact, there are 2 of them, as I mentioned. So now we are equipped with 2 types of sum rules. Crossing sum rules, which balance non-protected operators among themselves to give 0, And these sum rules which actually contain both protected and non-protected operators adding up to this number that we know. So let me present a first attempt to perform this optimization problem with these two types of sum rules. The protected part of the crossing equation is 0 because the protected part is crossing symmetric by itself. And then we only have, in terms of the low energy part, we only have this part coming from the two integrated constraints. Here we isolate Konishi, and then we have all the other states above Konishi. So now we carry on with our program where we try to find a linear combination of these sum rules, such as these quantities completely positive for every state above Konishi, is normalized to 1 or -1 for Konishi, such as we isolate the OP coefficient, and is extremized on this part of the protected part, which in this case are just given by the integrated correlators. Here are the results for the bounds that we obtained. So let me start here with the orange part of the plot. In the orange part of the plot, we first pretend that we only know one integrated correlator. That is just like an exercise to see how this optimization problem works if we just knew one integrated correlator. And you see that here we get an upper bound, which is this orange curve. However, the fact that I am shading all the rest by orange, it means that there is no lower bound. We don't produce lower bound in this situation with one single integrated constraint. It means all this area is an allowed area for the OP coefficient. However, things improve if we now use two integrated constraints. In this case, the bounds that we obtain are these blue curves, the upper and lower bound. And as you can see, at the strong coupling, it's narrow. However, well, so we can say that already at strong coupling, this optimization problem is working pretty well. But then as we move to a smaller coupling, intermediate value of the coupling, and especially weak coupling, then the allowed area becomes pretty bad. So we have a big range that where the OP coefficient could lie. But we are not done yet. This is just an exercise with these tools, but there is an extra tool that I would like to introduce. I thought that the best way to introduce this new type of sum rules would be to go to mailing space. So here I am starting with the correlation function in position space and performing a mailing transform to define what we call the mailing correlator. And we can also write, just like I presented the dispersion relation, this double discontinuity on the position space, we can also write a dispersion relation for the mailing correlator. In fact, the way that dispersion relation works is very much alike like the well-known case of the amplitude. Here you start by some trivial contour, and then you deform it, you pick up all the poles. This poles corresponds to the OP states, the OP intermediate states. And then you have this arc at infinity that fortunately we can drop because the mailing correlator has a good behavior at high energy when this Mandelstam variable goes to infinity. In fact, it's such a good behavior that even if we now stick in a polynomial, depending on this variable of integration, the integral will still be convergent, and that would lead to a new type of dispersion relation. By demanding that these two dispersion relations, one without the blue factor and the other with the blue factor, demanding that they are identical, that they should reproduce the same mailing correlator, then that provides us, the difference between them provides us a new type of sum rules, which now also contain some protected part and some non-protected part. This is what we call as anti-subtracted dispersion relations. Now that we include this new family of anti-subtracting dispersion relations, we do a better job at finding bounds. Let me start again by the orange, which is the case where we pretend that we just know one integrated constraint. The upper bound is pretty much the same. However, now we do obtain a lower bound at weak and intermediate coupling, although this is lost once we go to higher coupling. And the best bounds are still coming from the case where we know the two, where we input the two integrated correlators. In fact, the strong coupling part is pretty much the same as before, which means that in this optimization problem, the best bounds are still found from the integrated correlators and the crossing sum rules. However, now the cases, the region of intermediate coupling and weak coupling is much better. Now the gap that I showed before is closed, especially at weak coupling, and it becomes much narrow at intermediate value of the coupling. In fact, we can also compare this with our perturbative curve. So then you can see here the strong coupling and the weak coupling in green. Both of them pass through our bounds on the region of validity. and then on this crazy region, I mean, on the region where they become crazy, our bounds still provide some nice interpolation. Of course, the dream is to shrink these bounds such that we can eventually find the exact curve, maybe by including new type of sun rules. So, of course, a desperate question that we have is whether we can improve these bounds. And this may depend on the region of the coupling that you want to address, but let me address this question on this strong coupling region, the region of large G, where the CFT bootstrap problem becomes a simpler problem. As we know through holography, our 4-point function stress tensor should be dual to scattering of gravitons in IGST25. And especially when we take the strong coupling limit, if you follow this dictionary between the parameters on CFT and in ADS, the limit of large G corresponds to the limit of large radius of ADS. And in fact, what this means is that the amplitude in ADS now can be approximated by a flat space amplitude. And our CFT bootstrap problem reduces to a flat space matrix bootstrap problem, maybe similar to what we saw in the morning from Andrea. This problem is simpler than our CFT bootstrap problem, and we can use it as a toy model to address this question of whether the bounds can be improved. In fact, just to tell you a bit more about the dictionary, if you consider the low energy expansion of the amplitude, of the flat space amplitude, you get these low energy coefficients. And there is a map between these low energy coefficients and what we call integrated correlators. So the knowledge of our integrated correlators in this side of the flat space symmetric bootstrap is the knowledge of is equivalent to the knowledge of these first two low energy coefficients. These problems become the same and the bounds approximate as G is large, but in fact not only the bounds coincide when G is very large. Also the extremal positive functional, the functional F, this linear combination of our sun rules, also that one coincides. Here the blue line would correspond to the flat space, the output of our optimization problem in flat space, which would be equivalent to G equal infinity. And this you can see is very well approximated by these purple dots that corresponds to the evaluation of our CFT functional. So the problems become really identical, provided that you take G to be large enough. Now, given that the problems match at every level, bounds and functionals and every detail that you can think of, we can play with, do some experiments on the flat space case. And something, well, as I described, the flat space amplitude we are talking about here is a 5-dimensional flat space amplitude. But we can easily play with the dimensionality, just let's say, as an experiment. And in fact, what we find is that if we perform this optimization problem in flat space, but now in 10 dimensions, the bounds that we find on the coupling associated to this, in this case, would be a closed string and two gravitons, it becomes much tighter. The bounds are much better, well, are better in 10D than in 5D. So then you can ask the question of what does this experiment mean in terms of the CFT? So how do we recover the 10D flat space physics from the 4D CFT side? So the answer is just to consider not only the stress tensor, but also all the higher R-charge PPS operators, which are Kaluza-Klein modes of the graviton in S5. So this would be something that we hope we can address, and hopefully, and we have a hint from this exercise that will probably allow us to improve these bounds and get closer to the actual exact solution. So, okay, let me just summarize what we went through today in this presentation. So I introduced to you what we call dispersive sun rules, which are sun rules that are just saturated by single trace operators, which are operators that we know thanks to integrability. And in fact, there is a menu of this type of dispersive functionals. The simplest of them are just the crossing equation, but also I introduced these sun rules coming from these integrated correlators and also these anti-subtracted sun rules. The usefulness of them depends on the region of the coupling. As we saw, the strong coupling mainly, the job is done by the integrated correlators, and crossing is always there. You should never ignore crossing. But then a weak and an intermediate coupling, we also need the input of these anti-subtracted sun rules to get our best bounds. So we do get some two-sided bounds that interpolate all the way from weak to strong coupling. And as I described, there are some lessons from the strong coupling limit, where our CFT problem becomes S-matrix bootstrap problem. And we believe that from hints from this simpler limit, that if we consider mixed correlators that include Kaluza-Klein modes, then we would be able to improve these bounds. Also, here I just addressed the OP coefficient of Konishi, but in fact we can bound other observables. As long as these are observables that you can write as a sum rule of OP coefficients times this dispersive of Polyakov radio blocks, if you can do that for any observable, that will be something that we will be able to bound. So that includes the 4-point correlator itself and also other observables such as energy correlators. And of course, it'd be nice to see if we can perform this type of CFT bootstrap problem, dispersive CFT bootstrap problem, for other theories that are dual, that have open or closed string holographic duals, such as the theories that we will hear about tomorrow morning. Okay, thank you.
Thank you. Questions?
Hi. So you used this integrated correlators coming from BPS observable in deform theory, right?
Yeah, so they are computed from this partition function of this mass deform super young Mills.
So if you start from, say, a 2-point function in, say, I don't know, beta deform theory, but of two non-protected operators, but which become protected when beta is 0, and then differentiate twice to get some integrated correlators, and you can use a really non-trivial insight from integrability of beta deform probably as well. Like as an
right. Of course, well, we will have to make sure that that is independent from this integrated correlator. I mean, if it gives something new or is just redundant, but if it gives something new.
Because if you start from non-BPS 2-point function, right?
Yeah.
And then, because your integrated correlators are kind of very BPS-y, right?
Okay. Okay, I see what you mean. Yeah, so that is another way of improving our bounds. If we have more integrated correlators, that would certainly, I mean, as I was showing, one of the main points is that the integrated correlators do a very great job. There is a big difference even from considering 1 versus 2. So yeah, if you can do this, it would be great.
Other questions? If not, let's thank Frank again.
The microphone. Yeah.